Hello, here is a talk I gave at the North British Geometric Group Theory Seminar on January 22 of this year. So I thank again the organizers for their invitation to this very nice afternoon. And so let me talk about filtrations on the mapping class group of the punctured sphere. So here I begin with a statement of my main result. So first I need a bit of context. I'm interested in this group G. So G is the pure mapping class group of the sphere with n+1 points fixed. So I'm looking at isotopy classes of self-homeomorphisms of the sphere, fixing endpoints here, plus one base point. And so I'm looking them up to isotopy, and isotopies are asked to be through such homeomorphisms. And the pure, it's the pure version because I ask these homeomorphisms to fix my endpoints on the sphere, plus the base point. Okay, so this group acts on this fundamental group of the sphere with endpoints removed, and this is really an action because we asked this base point to be fixed. So this group here is basically the fundamental group of the plane minus n minus points, so it's free on n-1 generators. And this action here, this is the very natural action, the first one you can think of. And this action here is some instance of Artin action, as we shall see later. This is all the context I need to state my main result. So let me give you this main result. Here it is. If I take beta an element in my group and k an integer greater than 1, then beta is in the kth term of the lower central series of this group here, if and only if it satisfies this condition on the right, saying that it acts trivially modulo this k+1th term of the lower central series of the free group. So let me comment a bit about this. Going from left to right is easy, that's general theory. The difficult part is going from right to left, and it's also the most interesting part, because on the right you have a computable condition. Why is that computable? Because first you only have to check this condition for W in a basis of your free group, so this is a finite number of elements, n-1 elements, and then the lower central series of the free group is very well understood. So we can compute on the right, do a finite computation, and then we have an explicit condition for beta to be in this kth term of the lower central series. In fact, you can say exactly where beta is in this lower central series by this finite computation, and I will explain the computation right now. So basically, it amounts to computing the Milnor invariance of my element beta. So first, I have this Artin action, as before. So I take beta, an element of my pure mapping class group of the sphere fixing n+1 points. And then I get an automorphism of the free group, this fundamental group here. And this is not any automorphism, it has to be a basis conjugating automorphism. So this gives you elements Wi here of the free group, and so I must say that if you have a geometric description of your element beta, then getting this basis conjugating automorphism is just it's an easy thing to do. So now from these elements Wi, I will get formal power series, which are their Magnus expansions. So these elements are elements of the free group, so they are words in the xj and their inverses. So I will, from this, I will get a formal power series in some non-commuting variables big xj, just by replacing these little xj by 1 plus big xj, and their inverses will get replaced by the inverses of these formal power series. So let me get an example of that. Here I have a word in 3 generators of my free group. And so then I replace x1 and x3 with 1 plus big x1 and 1 plus big x3. And in the middle here, my inverse of x2 gets replaced by the inverse, the usual inverse of x plus 1 plus big x2 in formal power series. And so I get this formal power series, and what I'm interested in is in its coefficients, which are Milnor invariants of my element beta. So these coefficients are integers, and if I'm looking at monomials of degree d, then their coefficients are called Milnor invariants of degree d of beta. And so, okay, I take this -1 here because you see that it has to begin with a 1, but this is not really important. The important thing is that if I look at my condition, like before, this condition that beta has to act trivially on the free group modulo the k plus 1th term of the lower central series, then this condition is equivalent to Milnor invariance of degree strictly less than k being trivial. So to recap here, if I give you an element beta of my pure mapping class group, then I get a basis conjugating automorphism of my free group. So I get n-1 elements conjugating my xa. And these elements of the free groups, I can take their Magnus expansion, which gives me n-1 formal power series with coefficients in the integers. And so if I want to know where, if I want to know which condition is satisfied by beta, and so I just have to look at the first non-vanishing coefficients of these formal power series, and the degree of this first non-vanishing element coefficient will give me where beta is in the lower central series because of my previous theorem, which basically says that we can compute the lower central series from Milnor invariants. Now that I have introduced my main statement, I am going to first talk about braids and mapping classes and recall the relevant notions. So it will lead to an algebraic translation of the main theorem. So then I will have to introduce group filtrations and associated layerings before turning to a particular group filtration, which is the Andradekis filtration corresponding to Milnor invariance. And then I will explain a bit how we prove our main theorem, by which is exactly the Andradekis equality, the equality between the Andradekis filtration and the lower central series for our pure mapping class group of the sphere with n+1 fixed points. So let me talk a bit about the mapping class group of the punctured sphere, which is this one. So this is the isotopy, the group of isotopy classes of self-homeomorphisms of the sphere, permuting these n points, n marked points on the sphere, and fixing a base point. So inside this group, I have the pure mapping class group I'm interested in, which is the one where the self-homeomorphisms are supposed to fix the endpoints instead of just permuting them. And this mapping class group of the punctured sphere is a quotient of the usual Artin braid group. Why is that? That's because this braid group is the mapping class group of the disk with n punctures and fixing the boundary of the disk. That's the usual identification. And we have inside this mapping class group the pure braid group, of which our pure mapping class group is a quotient. So if we want to understand the groups on the left from the groups on the right, we have to understand the kernels. So what is the kernel of this quotient, and what is its intersection with the pure braid group? That's a cyclic subgroup. And so both kernels are generated by this xi-n, which is the full twist or the din twist around along a curve which is parallel to the boundary of the disk. So I will get back to the definition in a moment, but for the moment, let me just stress that this is a generator of the center of both the braid group and the pure braid group. So both these subgroups are in fact the same. They are the center of the braid group. Okay, so let me recap. This mapping class group of the punctured sphere is exactly the quotient of the braid group by its center, and we usually call it Bn star. And since I'm mostly interested in the pure version of that, the pure version is the quotient of the pure braid group by its center, and it's denoted by Pn star. Okay, so let me get back to the definition of this xi-n, which is the generator of the center of the braid group, or the pure braid group. So it's a pure braid, and as braid, it is the full twist, like that. And we can also look at it as a mapping class of the disk, fixing the boundary and fixing the endpoints. So here we take the din twist along a curve which is parallel to the boundary. So outside tubular neighborhood of this green curve, it does the identity, and in this neighborhood, it does exactly what is drawn here on this blue curve. It twists. We can also look at xi-n as an automorphism of the fundamental group of the disk minus endpoints. So at least there is an automorphism which is associated to it, and we'll see in a moment that this automorphism determines in fact xi-n. So here is a generator of this fundamental group. We have to take the base point on the boundary because we want the base point to be fixed. And here is its image by xi-n. And so this image is, well, you go around once, then you get along this little curve, and then you go back. So you have conjugated your generator by this curves going around once, which is exactly the product of all the generators of the fundamental group. So yes, you choose the names of the generators, just that this should be true, that this product of the generators corresponds to this element in this fundamental group. And so our automorphism here is conjugation by this element, this boundary element. Okay, so let me describe art in actions. So these are natural actions on fundamental group. If you look at your braid groups as mapping class groups, so the usual braid group acts on this free group, which is the fundamental group of the disk with endpoints removed. And there is a classical theorem by Artin saying that this action is faithful. So if you know the automorphism, then you know the braid. Okay, and then there is an identification of Bn with a subgroup of automorphisms of free groups, and we know exactly what subgroup this is. This is the subgroup of automorphisms fixing this boundary element, which is the product of the generators, and acting by conjugation on a basis, that is, each generator in a basis is sent to conjugate of another generator. Okay. So we have a similar situation for Bn star, which is this mapping class group here of the sphere. It acts on this fundamental group, as I said before. And so there is another classical theorem by Magnus this time, saying that this action is also faithful. And also we know the image, but I will get back to this later. This is because this second action can be seen as a quotient of the first one. So basically, geometrically, this quotient corresponds to crushing the boundary of the disk to a point, and then you get a sphere with n-marked points, and one mapping class here will give a mapping class here. It's the quotient I presented before. And so then we will determine the image of this action completely later during the talk. So now we have that our group, the group we're interested in, is acting faithfully on the free group. So it's a subgroup of automorphisms of free groups. And what we're going to do now is to describe a filtration on automorphisms of free group corresponding to Milnor invariance. This filtration, which is called the Andradekis filtration, is a particular case of a group filtration. So I have first to introduce some basic terminology about group filtrations and their associated lyrics. So let me first state what a group filtration is. For that, I will need first some notations. This is the usual commutator of two elements in a group. This notation, which I will not use much, only on the next slide, is the exponential notation for denoting the left and the right action of the group on itself by conjugation. And as usual, if we take two subsets of our group, A and B, then bracket of A and B is the notation used to denote the subgroup generated by commutators of elements of A with elements of B. Okay, let me say what a filtration is. So a filtration on a group G is a nested sequence of subgroups beginning with the for group, and then taking smaller and smaller subgroups. And we ask for this condition, which is a centrality condition, saying that if you take the commutator of an element of gi with an element of gj, then you go inside ga plus j. So the lower central series of a group is one fundamental example of such a filtration. So it is such a filtration. Let me give you, remind you rapidly of the usual definition. So we begin with the whole group, and then at each step, we take the commutators of the whole group with the previous step of the filtration. And this is the minimal filtration on a group G, by which I mean that if I have a filtration on a group G, then each step of this filtration will contain the corresponding step of the lower central series, which means that it's minimal for inclusion of filtrations. So why are such filtrations very important? That's because we can study it through their associated graded, which are Lie rings, that is Lie algebras over Z. So if I have a filtration, I can take the quotient of gi over gi plus 1. This is an abelian group because of the centrality condition. And then I will take the direct sum of all of these graded these abelian group, and this gives a graded abelian group, and we give it a name which is L, like Lie ring or Lie algebra. So where does the Lie structure come from? It comes from commutators in G. So if I take commutators in G, it will give a well-defined graded map going from the product of L to itself with L. And we have formulas in groups giving formulas in the associated graded. For example, we have this formula, which will give you the antisymmetry of this bracket. And we have this formula giving the bilinearity, and then we have another formula which is called the Witt-Hall formula, which gives exactly the Jacobi identity, and then we know that this associated, induced map is a Lie bracket on this associated graded, which is then a Lie algebra over Z, a Lie ring. Okay, so let me talk briefly about Lie rings of groups, by which I mean Lie rings associated to lower central series of group. What I'm saying is if I don't say explicitly which filtration I'm taking on a group, then it's by default the lower central series. And here is this very famous theorem by Magnus saying that if we take the free group and you take the Lie ring associated to its lower central series, then it is free on n generators. Let me remark that in general, the Lie ring of a group can be very difficult to compute when it's in trivial. Now that we have introduced group filtration, I will talk about this particular filtration on automorphisms of free groups, which is the Andradekis filtration, and get to the Andradekis problem, of which our statement is a partial answer. So the Andradekis filtration first. It is a filtration not directly on the whole group of automorphisms of the free group, but on a subgroup which is denoted by IAN. So this subgroup is this kernel, which means that these are automorphisms acting trivially on the abelianization. AA is for identity on abelianization. And so on this subgroup, we have two filtrations. The first one on the left is the lower central series of this group. And the second one is the Andradekis filtration. So IAN is the first one, and then we have A2, A3, etc. And these are defined by the following formula, which means that AK is the subgroup of automorphisms acting trivially modulo the k+1th term of the lower central series of the free group. So this is a filtration in my sense, that is, it satisfies this centrality condition. And since the lower central series is the minimal filtration on IAN, we get these inclusions here. And these inclusions are the main object of the Andradekis problem. But before going into that, let me give you a quick remark about residual nilpotence. We know that the free group is residually nilpotent, which means that the intersection of its lower central series is trivial. So a direct consequence of this is the fact that the intersection of the AK of the Andradekis filtration is also trivial, because if you are on in AK, then it means that each element of the free group gets sent to itself times some element in the k+1th term of the lower central series of the free group. And if you are in all the AK, then this element must be trivial, so there must be multiplication by 1 on each element, so you must be the identity. And the fact that the Andradekis filtration has trivial intersection implies that, because of these inclusions, that the lower central series here also has trivial intersection. And this fact means that, in fact, you can really study effectively IAN by looking at filtrations, because basically filtrations will see the structure of the whole group, whereas, for example, on automorphisms of the free group, filtrations will stop very early, so you won't be able to see much of the structure inside filtrations. So that's the main reason why we are looking at IAN, automorphisms acting trivially on the abelianization, and that is also the main reason why I'm talking about pure braids and pure mapping classes, because they also will satisfy this condition, because they will be subgroups of IAN. So now let me talk about this inclusion between the lower central series and the lower central series of IAN and the Andradekis filtration. So it was originally thought that they would be equal, these inclusions would be equalities, but more than 50 years later, there was an answer by Bartholdi claiming that he had a counterexample, and but he still thought that they would be the same up to finite index. And the fact is that not even that is true. So this uses a lot of computer calculations, notably by Day and Putman, who computed an infinite presentation of IAN. And from this, we can get computations of the ranks of the associated graded for a very small k and very small n, and see that they are different. So we don't have this equality even up to finite index. But in general, this is a very difficult problem, and we do not understand how the difference between the filtrations behaves. So one way to look at this problem and to get simpler problem from this very difficult one is to get restriction to subgroups. And so if G is some subgroup of IAN, we will restrict the filtrations. So we get 3 filtrations on this group, actually. We get a filtration on the restriction of the Andradekis filtration, the restriction of the lower central series of IAN, and then we get inside them the minimal filtration on G, which is its lower central series. So the question is, when are these filtrations equal? And the answer is not always. Obviously, what I mean by obviously is if you think about it and you take very simple subgroups like cyclic groups, then you will find counterexamples right away. And even if you think a little bit harder, but not that much harder, then you will get a huge variety of counterexamples. So the thing is that you can hope for these filtrations to be equal only if your subgroup is kind of well embedded inside IAN. And when these filtrations are equal, we say that G satisfies the Andradekis equality. Here is one theorem. For G, the pure braid group, which we saw before, which is this mapping class group of the disk with n points fixed, because it's the pure one, and the boundary also fixed, acting faithfully on this fundamental group. So it identifies with a subgroup of automorphisms of this free group. Then we have the Andradekis equality. In fact, if we are taking pure braids, so it identifies with a subgroup of IAN, and we are in this situation, and then we can recognize the lower central series of the pure braid group from, as we can identify it with this restriction of the Andradekis filtration. So this theorem, I gave a direct proof in my thesis, but it could be obtained by from these 2 papers. So Habiger and Masbaum showed that Milnor invariants, which are encoding this restriction of the Andradekis filtration, were universal finite type invariants. And then Mostovoy and Villerton showed that finite type invariants were in fact separating braids up to the right step of the lower central series. So with gluing these 2 results together, you get that you have this Andradekis equality, meaning that Milnor invariants are in fact looking at the lower central series of the pure braid group. And what we are interested in here is to do exactly the same, but for the pure mapping class group of the sphere, which is the quotient of the pure braid group by its center acting on the free group on n-1 generators. So in order to do that, to get this Andradekis equality, then we want to translate our problem in terms of Lie algebras over Z, that is, in terms of Lie rings. So for doing that, we have this Johnsonmorphism. So from this action of IAN on the free group, the canonical action, we get an action of the associated graded on the layering associated to the free group, which is free on n generators by the theorem of Magnus that I quoted above. And an action of Lie algebras is exactly is an action by derivation. This was an action by group automorphisms, an action in the category of groups, and here we have an action in the category of Lie algebras, which means exactly that we have some morphism going from this associated graded to the Andradekis filtration, going to derivations of the free Lie ring. And this is the one which we call the Johnsonmorphism, and it is injective by definition of the Andradekis filtration. In fact, if you look at the condition for an element here to be in the kernel, you see from this definition that it has to be trivial. So this Johnsonmorphism has to be injective. And there is an explicit formula for this Johnsonmorphism, which is well known to those of you who are dealing with mapping class groups, because this is the definition of the Johnsonmorphism for mapping class groups, which is this explicit formula here. And so from this, we will be able to translate our problem in terms of Lie algebras. And so our problem is the Andradekis equality for some subgroup of IAN, which is this question: is the restriction of the Andradekis filtration equal to the lower central series of the group? And in fact, this is equivalent to the induced morphism between the associated graded, so this is the layering associated to the lower central series, this one is associated to this one, or which we can replace by the whole Andradekis filtration, because we haven't, it's just the restriction of some filtration, so we can do that. And so let me give you the proof of that, because this is an example of the kind of proof you get when dealing with group filtrations. So if you take an element which is a counterexample to this equality here, so which is in this kth term of the Andradekis filtration restricted to G, but not in the kth term of the lower central series of G, then this element must be in some gamma j and not in gamma j plus 1 for some j less than k, because it's not in gamma 1. It has to be in gamma 1 because gamma 1 is the whole group, but maybe it's in gamma 2. It's not in gamma 2, and then you can take j equals 1. But if it's in gamma 2, maybe it's not in gamma 3, and you can take equals 2. And if it's in gamma 3, etc. And you know that it's not in gamma k because of our hypothesis. So you have to find it somewhere in the lower central series before gamma k. Okay, and if it's in gamma j and not in gamma j plus 1, that means exactly that it gives a non-trivial class in this quotient. But then its image in this quotient here would be trivial. Why is that? Because we know that x is in AK, and AK is in gamma j plus 1, so it's 0 inside this quotient. So this would give, from a counterexample x here to this equality, you get a non-trivial element in the kernel of this map. And the other way around is the same but easier. If you have an element in the kernel here, you can get directly counterexample of this one. So these are equivalent, and then we can compose this map with this one, and this Johnsonmorphism is injected. So this is equivalent to the this composition with the Johnsonmorphism to be injective. And this one we will we will call it only tau, which is the Johnsonmorphism for this subgroup G. And so this is the translation I was looking for. The Andradekis equality for G is equivalent to this Johnsonmorphism for G being injected. So now we turn to the Andradekis equality for this Pn star, which is this group we're interested in, which is the pure mapping class group of the sphere fixing n+1 points. So let me give the main result, which I reformulate like this. For this group, this mapping class group, acting faithfully on this fundamental group, which is free on n-1 generators, then the Andradekis equality holds, which means that we can recognize its lower central series as the intersection of the Andradekis filtration with this subgroup of IA n-1. Okay. So another way to say that is the way I said it at the beginning, which is if I have an element of my subgroup, it is in the kth term of the lower central series if and only if it acts trivially. It is in AK, which means that it acts trivially on the free group modulo its this k+1 term of the lower central series. And yet another way to say that is to say that the associated Johnsonmorphism is injective. So in particular, this layering associated to the lower central series of this group identifies to a sub-layering of derivations of the free Lie algebra. And moreover, generators are known because such a layering associated to a lower central series is always generated by its degree 1. So you just have to look at this map in degree 1 and see what derivations you get. And in particular, the free layering is without torsion. So derivations of the free layerings is without torsion too, and so a sub-layering has to be without torsion. So there is no torsion in the lower central series of this group. Okay, so to show this, to prove this theorem, we have to use a decomposition of this group. And so I'm getting back to what I said about Artin actions, that the Artin action for this group is the quotient of the usual one for braids. So let me remind you of what was true for braids. So for braids, we have that the pure braid group identifies with automorphisms of the free group acting by conjugation in a basis and fixing this this boundary element. So it sends every generator to a conjugate of itself, and it fixes the boundary element. Okay, so now we will describe this quotient of killing the boundary, crushing the boundary of the disk to one point to get a sphere. This quotient has an algebraic description like this. So this action here induces an action on this quotient where we kill this boundary element, because the boundary element is always fixed. So you can kill it and still get an action. And this group here, so killing the boundary element is equivalent to this relation, which can be rewritten like this, which is like this. And this allows us to eliminate this generator, so we get the free group on n-1 elements. Okay. And so this action factors through the quotient of Pn by its center, because we've seen earlier that the central element acts by conjugation by the boundary element. So if you kill this boundary element, then this conjugation becomes trivial, and so you have a factorization by that. And you know from the theorem of Magnus that I quoted earlier that the induced action is in fact faithful, so that in fact this quotient by the center was exactly the quotient by the kernel of this action here. So what automorphisms do we get? We get automorphisms acting by conjugation on the generators. So these WAs here are not exactly the same as here. You have to eliminate xn by this relation, but still we have basis conjugating automorphisms. This condition here becomes trivial because if you kill the boundary element, you replace this by 1, and 1 is always fixed by an action by automorphisms, so this one is trivial. But there is one condition left, because here we have also a condition for xn, and xn in the quotient is identified with this inverse of the boundary element. So the fact that here xn has to be sent to a conjugate of itself means that here the boundary element must be sent to a conjugate of itself. So this gives, if you look at these conditions, this one is a little bit weaker, which means that it defines a larger subgroup than Pn-1. So Pn-1 are the ones satisfying these conditions but fixing the boundary element. And if you want to send the boundary element to conjugate of itself, you have to compose a pure braid with an inner automorphism. And so this group is the product of these two subgroups, which is the decomposition we will use. So now we get to a theorem allowing us to use this decomposition as a product of subgroups to decompose filtrations on the subgroup we're interested in. So the theorem goes as follows. K is a subgroup of IAN. Then we get an associated Johnsonmorphism. We suppose that first we know that the Andradekis equality is true for K, which means that tau is injective. And we also suppose that we have this technical condition saying that every element in the image of L of K, so inside derivations of the Fourier ring, this intersection of this image with inner derivations equals comes from an element in K, which is also an inner automorphism via the Johnsonmorphism. So if we have this and this technical condition, then the product of K by the subgroup of inner automorphisms also satisfies the Andradekis equality. So this theorem is a particular case of a more general result of decomposition of filtrations. And this is a rare result. In fact, this is the only result I know of allowing us to go to get from the Andradekis equality for a subgroup to the Andradekis equality for another subgroup. Because usually the problem is that if you have two subgroups, then the lower central series won't be compatible, And if you know that the Andradekis equality is true for one, getting the Andradekis is true, getting the Andradekis equality for the other one is usually very not easier. And here we have exactly this situation where we have the Andradekis equality for K, and then we get this Andradekis equality for this product. So this is a very rare result in that sense. And so let me end by applying this theorem to Pn star. So we have Pn star, we identify it as a subgroup of IAN-1 via the out-in action. And we have, we have just seen this decomposition as the product of the pure Bray group on N-1 generators with inner automorphisms. So we need to the hypothesis of the previous theorem. So we know that the Andradekis equality is true for pure braids. This was the theorem that I quoted earlier, which was could be deduced from work by Masbaum, Habeger, Masbaum, and Mostovoy, Vellerton. So this is true. And so we have to check the technical condition. So let us see if we have some element here, which is in this intersection. This is a derivation, and it's in this image. It comes from a braid, from a pure braid. So it has to fix this boundary, this class of the boundary element. Fixing it in terms of Lie algebras, which means it has to be sent to 0. And also it is inside this one, so it's an inner derivation. So if it is an inner derivation, then the thing is that W has to commute with this element, and since we're in the free Lie algebra, then W must be a multiple of this element. And we know that the inner derivation associated to this element is the derivation induced by the central element of the pure Bray group, so that here we have only multiples of this derivation induced by this element. And then what I said at the beginning was that this central element is acting by conjugation by the boundary element. So it is indeed inside this intersection with inner automorphisms, and we have exactly the condition, technical condition we needed to apply our previous theorem and say that this group satisfies the Andradekis equality, which means that its lower central series can be detected by Milnor invariants. Okay, that's it. Thank you for watching.